Assalamualaikum everyone and a very good day to all. In this video, we shall learn about transmission impairment. This means that the signal at the beginning of the medium is not the same as the signal at the end of the medium. This video will discuss about attenuation, distortion, and noise that can impair a signal. This is the second installment of a three-parts video for chapter 3. Here is the table of contents for you to navigate through this video. Okay, let's go to transmission impairment. Basically, as signals travel through transmission media, they became imperfect. Okay, this imperfection causes a signal impairment. And what does it mean? It means that the signal at the transmitter at the beginning of the medium is not the same as the signal at the end of the medium, which is what they received. Okay, so there are three basic causes of impairments, and they are attenuation, distortion, and noise. Okay, what does attenuation means? Attenuation means a loss of energy when a signal, either a simple or composite. Okay, what composite means? It means composed of different elements or different signals with different frequencies, for example. Okay, so when a signal they travel through a medium, some of them lose some of this energy in overcoming the resistance of the medium. Okay, that's why you can feel a wire that is carrying electric signals. They get warm, okay, sometimes even hot, okay, after a while. So this electrical energy in the signal is converted to heat. To compensate for this loss, amplifiers are used to amplify the signal back again. Okay, so you can see in this figure where you can see that the original signal, after some time after transmitting certain length of medium, it becomes attenuated. The energy has weakened and the energy has converted into heat. So we need amplifier where we can actually amplify the signal again to its original signal. In attenuation or in any kind of performance of a signal, that we need to measure it in decibel. Okay, what is decibel? Decibel is a unit to show that a signal that has lost or gained strength. Okay, so typically engineers use the unit of the decibel. The decibel, or sometimes also known as dB, okay, measures the relative strength of two signals or one signal at two different points. Note that the decibel is negative if a signal is attenuated and positive if a signal is amplified. So you can see here we have a dB equals to 10 log 10 P2 over P1, where P1 is the input signal and P2 is the output signal. So it will be output over input. Here is the typical, that one is in terms of power, okay, but sometimes there are people who are using it in terms of voltage, okay, instead of power. So in this case, because the power is proportional to the square of the voltage, so the formula is dB equals to 20 log 10 V2 over V1, where V2 is the output signal and V1 is the input voltage. Okay, so in the rest of this course, we express dB in terms of power, unless indicated otherwise. Sometimes the decibel is also used to measure signal power in milliwatts. In this case, it is referred to as dBm and is calculated as dBm equals to 10 log 10 PM, where PM is the power in milliwatts. This is an example for decibel on how we can use decibel. Suppose that a signal travels through a transmission medium and its power is reduced to 1/2. Calculate its attenuation. So right away you can see that this is an attenuation because the power at the output signal is reduced. It has been attenuated. Okay, so let's calculate. This means that P2 is a half P1. Okay, so P1 is P1, whatever the value. Okay, so P2 is half of that. So in this case, the attenuation or loss of power can be calculated as 10 log 10 P2 over P1. You just substitute P2 with 0.5 P1. Okay, so cancel out P1, you get 10 log 10, 0.5. And just multiply and you get minus 3 dB. So this P1 is the input signal, P2 is the output signal, and minus 3 dB, the minus indicate loss of power. So be careful and make sure that you are familiarized with how to use your calculator on getting this kind of equation. Let's see another example. Okay, one of the reasons why engineers use decibel to measure the changes in the strength of a signal is because decibel numbers can be added or subtracted when we are measuring several points, like in cascading instead of just two, with more than just 2 points. So in this figure, you can see that we can calculate the cascading points in the figure as the signal travels from point 1 to point 4, and we can see that signal is attenuated by the time it reaches point 2, and between points 2 and 3 the signal is amplified. Again, between point 3 and 4 the signal is attenuated. Then we can find the resultant decibel value for the signal just by adding the decibel measurements between each of the points. Okay, so where the attenuation that happened, then it is minus 3 in this example, and then when it is amplified, then you have to plus them, and again when it's attenuated, then minus 3, and then the end result will be plus 1. And this plus will show that it is being amplified, meaning that it is gained in terms of power. Let's do another example when it is involved with dBm. Calculate the power of a signal with dBm equals to minus 30. So remember just now we saw that dBm equals to 10 log 10 PM. Okay, so we can calculate the power. We need to find the power of this signal, right? So we can reverse it and do it as dBm equals to 10 log 10 PM equals to minus 30. And then log 10 PM equals to minus 3, as you cancel out the 10, and PM equals to 10 to the power of minus 3 milliwatts. Okay, so again, familiarize yourself with how to do this kind of a question. Decibels per kilometer or dB per kilometer is typically used to define loss in a cable. So let's see this example. If the signal at the beginning of a cable with minus 0.3 dB per kilometer has a power of 2 milliwatts, okay, at the beginning, what is the power at the signal at 5 kilometer? So minus 0.3 dB per kilometer is the loss in that particular cable. So you need to measure the power after it travels 5 kilometer. So you can see that the loss is 5 times of minus 0.3 dB per kilometer. Again, you can see that 5 kilometer and the minus 0.3 dB per kilometer will cancel out the kilometer and you'll get minus 1.5 dB, just to check. And then you can calculate the power as dB equals to 10 log 10 P2 over P1. Okay, so it is equals to minus 1.5. And now we can find the P2 over P1. Okay, as you can see here, you need to make sure that you know how to invert the log 10. Okay, to the other side, it will become 10 to the power of minus 1.5. So if you solve this, then you'll see that the power is P2 over P1 equals to 0.71, and P2 will be 0.1 times P2. P2 equals to 0.71 P1, and we know that P1 equals to 2 milliwatts, so you multiply together and you get 1.4 milliwatts. Okay, let's go to the next cause of impairment. Okay, distortion. Distortion means that the signal changes its form or shape. Distortion can occur in a composite signal made of different frequencies. Each signal component has its own propagation speed through a medium and therefore its own delay in arriving at the final destination. Differences in delay may create a difference in phase if the delay is not exactly the same as the period duration. In other words, it means that the signal components that the receiver has have phases different than from what they had at the sender. Okay, the shape of the composite signal is therefore will be different. It's not the same. And in this figure, it shows the effect of distortion on a composite signal, where you can see in a composite signal, it is consists of different elements, in this case components, and with different phases. So when they combine, some will arrive at different frequency, different time. There's a delay, and this will cause the imperfection in the signal received. Noise is the other cause of impairment. Several types of noise, such as thermal noise, induced noise, crosstalk, and impulse noise, may corrupt the signal. Okay, example of thermal noise is like the random motion of electrons in a wire, which creates an extra signal not originally sent by the transmitter. And then we have induced noise that comes from sources such as motors and other appliances. Crosstalk is the effect of one wire on the other. One wire acts as a sending antenna and the other as the receiver antenna. And we also have impulse noise, which is a spike or a signal with high energy in a very short time that comes from power lines, lightning, and so on. So in this figure, it shows the effect of noise on a signal, where you have the very sharp signal in the noise. As we will see later on in this video, we need to find the theoretical bit rate limit, and we need to know the ratio of the signal power to the noise power. Okay, signal to noise ratio is used to measure the quality of a system. It relates to the other impairment that we just saw just now, noise. It also indicates the strength of the signal with respect to the noise power in the system. It is the ratio between two powers and usually given in dB and referred to as SNR dB. So the signal to noise ratio is defined as average signal power over average noise power. We need to consider the average signal power and average noise power because this may change with time. So we cannot just take instantaneous signal power or instantaneous noise power. Okay, this figure shows you the idea of SNR or signal to noise ratio. SNR is actually the ratio of what is wanted, and which is the signal, and to what is not wanted, which is the noise. A high SNR means that the signal is less corrupted by noise. A low SNR means that the signal is more corrupted by the noise. Because SNR is the ratio of two powers, it is often described in decibel units, SNR dB. So in this figure, you can see the two cases of SNR where we have a high SNR and the bottom one is the low or small SNR. Okay, let's do an example on SNR. Given the power of a signal is 10 milliwatt and the power of the noise is 1 microwatt, calculate the values of SNR and SNR dB. They can be calculated as you just divide the average signal power divided by average noise power, and I change it. I multiply both with 1000 to make it both into milliwatts. But just be careful. Okay, so you know milliwatts is just basically 10 to the power of -3, and micro is 10 to the power -6, and you should be okay. You get 10,000. So now you can calculate SNR dB, which is 10 log 10 of SNR. You just multiply them and you get 40. Let's see another example for signal to noise ratio. Find the values of SNR and SNRdB for a noiseless channel. When we talk about noiseless channel, we will see that it means that the average noise power equals to 0. So we can calculate the SNR by dividing signal power with 0 and get infinity. Same goes to SNRdB, you will also get infinity. Obviously, we can never achieve this in real life, as this is an ideal theoretical scenario only. Before I end this video, please let me know how is your understanding on this topic throughout this video so far at this link. Your participation is highly appreciated. If you have any questions or comments, please let me know. Thank you and see you on the next video.